Okay, so today's topic is polygon interior and exterior angles. And we're going to be looking at the things that we've already been doing for triangles, but we're going to be doing them with polygons that have more than three sides. A triangle just has three sides. Now we're going into 4, 5, 6, and even more sides. Interior angles are just the angles that we've always known. They're just the angles inside of a polygon that we spend most of our time studying. Exterior angles, we learned about with the exterior angle theorem for triangles, but now we're just going to do the same thing with polygons that have more than three sides. So we're going to start by looking at triangles, and as you're going to see, everything in geometry, in flat geometry, what's called planar geometry or planimetry, everything kind of boils down to triangles. So let's start with a nice big triangle here. Okay. So we have a triangle, and if you notice, there's no way for me to split this up any farther going between existing vertices. If I was going to kind of divide up the middle a little bit here, I would have to go to it. I would have to add a new point. I'd have to add a point D somewhere there, because if I tried to move D and move this into an existing point, it's just going to slide back onto that side, right? So if I want to divide up the interior of this triangle anymore, I have to come up with a new point. I can't do it with my existing points. And so because of that, we say that a triangle is kind of the base figure, the base two-dimensional figure, because anything less than three sides just collapses into a line. And so three sides is kind of like where we're starting, okay? So now we're going to put this over to the side, and now we're going to look at the next type of, we're going to add a side and get four sides, okay? And notice I'm not going to be doing any of this with regular polygons. Now you can do that. I'm going to show you regular and non-regular, but I'm not trying to make this pretty or some kind of a special case. This is going to be the same case for all convex polygons. Okay, so here I have some quadrilateral. Okay, and now notice that I can add a line segment from here to here, and it actually does divide the interior of that quadrilateral down into two triangles. Okay, so we've divided up the four-sided shape into two three-sided shapes. Okay, and of course the same thing would happen with a regular quadrilateral, like a rectangle or a square. Now let's see if I can just do this with like 1, 2, 3, 4, 5. Okay. So there's a five-sided pentagon, not a regular pentagon. We could certainly do it with a regular pentagon. But here I'm going to add these segments in, and notice that I can divide this up into two or three. Using two lines, I can divide that Pentagon up into three triangles. Okay, so let's just recap here. When we had four sides, we could divide it into two. When we have five sides, we can divide it into three. Okay, so let's do this. I'm going to add a little text box here. This had three sides and one triangle was possible. Okay, so that was that. Then we came up here. And we had four sides and 2 triangles. Okay? So that was possible there. Now we're going to have 5 sides and 3 triangles. Okay? So you're probably starting to get the picture where we're going with this, but let's do another one. Next to 6 sides. 1, 2, 3, 4, 5, 6. So there is a hexagon, and I can divide this up into 1, 2, 3. So I have 4 triangles. 1 here, 2, 3, and 4. So now we're going to have 6 sides gives 4 triangles. Okay, we'll do one more just to make it really clear. So next would be 7. 1, 2, 3, 4, 5, 7. You have to be careful here. It has to be convex, because if you start doing this other kind of thing, it's going to throw off the logic here. Okay. So there's 7, adding in. Convex or concave polygons have kind of some of their own rules. 1, 2, 3, and that's because 4, and that's because they have their interior angles, which we're actually going to be learning about. Their interior angles are different when they're concave. So we're saying that for this, see how if I was to make this concave by like bringing it up here, all of my lines turn out to be, they go outside of the polygon. So that's why we have to make sure that it's convex, so that it retains this kind of, you know, you could even do it there, I guess, but maybe I need to think about that more. And if I move this, maybe if I choose a different point as my starting point, it would still work. But anyway, that's a discussion for another day. So as you can see here, I've got a heptagon with 7 points. 1, 2, 3, 4, 5. So now we've got 7 sides gives 5 triangles. So what's the relationship here, right? We've got to ask ourselves, what's the relationship? 7 sides gives 5 triangles. 6 gives 4. 5 gives 3. 4 gives 2. 3 gives 1. What's the pattern? Well, it's the number of sides minus 2, right? So that's what we're looking for here. Number of sides minus 2. That's what we're looking for here. Number of sides minus 2. And so we're going to learn more about that in just a second. So let's think back to what we know about triangles. So this triangle, the sum of its interior angles is pretty obviously, let's do angle. I need to just get the polygon. Oops. Okay. All right. So if we took this angle of 110.27, this one 49.22, this one 20.51, we added all those up, we would get 180 degrees, right? That's what's in the triangle. So then let's move on here. So then, by that logic, this triangle here has an interior angle sum of 180 degrees. So then what about this triangle? It's also a triangle, so it's also 180 degrees. So what's the interior angle sum of the quadrilateral? Right, it's 360 degrees. So the triangle has 180 degrees total interior angle sum. We'll just call it interior angle sum. Okay, 180 degrees interior angle sum. And now we've got this quadrilateral that has 360 degrees interior angle sum. And now we've got this pentagon. That triangle has 180, that triangle has 180, that triangle has 180. So you can kind of see where we're going with this. It's going to be 3 times 180, which is 540. So what you're seeing here is this. Let's look at the whole picture now. What you're seeing here is this. Okay, and I just marked these by accident out there. When you have one triangle, when you have 3 sides, it gives you one triangle. That triangle has 180 degrees interior angle sum. When you have 4 sides, it gives you 2 triangles. Each one of them has 180 degrees, so that means together you get 360. 5 sides gives you 3 triangles, each which has 180 degrees, so your total interior angle sum is 540. This is going to continue, okay? This is going to continue. So, so we need to generalize this and say what the formula is. So we can do that here. We can say that the interior angle sum of a polygon with n sides is the interior angle sum S of a polygon with n sides is S equals, and look down here, don't look at, I'm going to put some coding up here. S equals (180), because that's how much was in each triangle, times n minus 2, where n is the number of sides, right? 180 times n minus 2. So there is our formula. It's 180 times n minus 2. So then if it's a regular polygon, so now we're going to come in here and just look at regular polygons. So notice that that was the number of sides minus 2. We figured that out pretty well. If it's 6 sides, it gives us 4 triangles. Each has 180 degrees, so that'll always work. Now we're going to work on just regular polygons, So if I have 3 vertices, I have this, okay? So we already know that each of these angles is going to be 60 degrees, right? Because it's an equilateral triangle, 60, 60, 60 has to be 180 right there. Okay, so each of the angles has to be the same. What if I go here now, let me do another regular polygon, and give it 4 sides? Well, of course, that gives me a square, right? I'm just going to move this. Move this whole thing down. So that's going to give me a square. I know that each of those is 90 degrees. What if I did a regular pentagon? Okay, well, I need to start figuring out what this is. So let's look at what our formula tells us, right? The formula tells us 180 times n minus 2. Let me copy and paste this down here. 180 times n minus 2 is the sum of the interior angles, all of these angles in here, right? But I know that that's 90. So let's talk about what this S would be. So S equals 180 times 4 minus 2, okay, which is 180 times 2, which is 360. But if the angle sum here in this square is 360, and there are 4 angles, they have to all be the same measurement, right? So then each angle equals 360 divided by 4, which equals 90. That's how we get that 90 right there, okay? So let's move on to this. Let's move on to this one down here, the Pentagon, okay? Oops, keep clicking the wrong thing. Okay, let's move on to the Pentagon. So this would give me S equals 180 times 5 minus 2, which is 180 times 3, which is 540. Okay, that's going to be for that one. But now I'm going to say, well, each angle is 540 divided by 5, because there's 5 of them, right? And that's going to give me 108. So now we see that each of these angles is 108. Okay? And so next we're going to look at a regular hexagon. Okay, regular hexagon. 6 of those. Woo, I made that big. Let's see if we can drag that down a little bit here and size it down a little bit. Okay, regular hexagon. So the formula tells us we're looking at S equals 180 times 4 minus 2, or excuse me, 6 minus 2 is 180 times 4, which is 720. Okay, I think that's right. I'm just double checking my numbers real quick. 180 times 4, yeah, 720. Okay, so then each angle, each of those angles has to equal 720 divided by 6, which is 120. Okay, so we're kind of figuring this out here. So each of the angles has to be the same thing because it's all regular. So let's talk about what this means in terms of our formula here. So this is the total exterior, the interior angle sum. So now we're going to come up with a new formula for the measure of each interior angle of a regular polygon. It has to be a regular polygon, okay? And all of that is going to equal this. It's going to equal 180 times n minus 2 over S, over N, over N. So there's our formula, 180 times n minus 2 that we had before, but now we're dividing it by the number of sides because the number of sides equals the number of angles. And so that is what we're ultimately going to be seeing here, is this. Okay? We're ultimately going to be seeing this, that each of, that looks terrible, that each of the interior angles has to be the same if it is a regular polygon. And so each of them is going to be the same. We're going to take the sum of the interior angles and divide by 2. Now the next thing we need to look at is these exterior angles. So the next thing we're going to look at is these exterior angles. So let's talk about what an exterior angle looks like in a triangle. Let's just make a triangle here. Okay, we have some triangle. We know that the exterior angles, and remember when we did this back in the fall, that the exterior angles look like this. So we're basically picking a direction to do this, and we set all of these things up so that we have the lines that they're contained in, okay? And, well, let me even just do this a little bit differently. I'm just going to do this with segments, or rays, rather. We just pick a direction to do this, and then we do it the same direction around all of them. And remember my example about the spokes of the car wheels? I don't want them clashing. So, for example, if I've done my first one like that, or first two like that, I can't then, on this one, I can't, come back around and do it this way, because then my spokes are clashing up here, right? So I want to keep everything flowing the same direction, and then these angles here are what I'm going to have. Oops. These angles here are what I'm going to have as my exterior angles, and notice they're all going the same direction here, okay? And then the difference is that we already know that these are going to add up to 360 degrees, because we can see right here that each of these is a supplement to the angle that was in here. So whatever was in here, I'm going to get rid of these labels on these segments because these are really annoying. Okay, label, no, I want to get rid of all those. No, I want to get rid of these is what I want to get rid of. Show label. Okay. So, for example, this angle here, where my pointer is, would have been some angle, but that 54.56 is its supplement. The same goes for this. The interior angle of the triangle would have been something, but this is the supplement of it. And the same thing goes for out here. So I'm going to switch over to my paper and I'm going to write some work out, and I want you to see if this makes sense to you. Okay, so I've got a triangle here and I've drawn the exterior angles in. I'm going to show you how we can do this with general case, okay? So let's say that this angle here is A, this is the interior, this angle is B, and this angle is C, okay? So I know then that this exterior angle right here is going to be 180 minus A. This is going to be 180 minus B, and this is going to be 180 minus C, okay? Just using the supplements there. So then the exterior angle theorem, or the exterior angle sum, is just the sum of those. It's going to be 180 minus A plus 180 minus B plus 180 minus C. Okay? So then just using our algebra skills, we can get rid of all this. Okay, I'm going to collect some terms here. 180 times 3 minus A minus B minus C. Well, 180 times 3 is 540 minus A minus B minus C. And then I'm just going to factor out here a negative 1. Okay, but we know, but what does this equal? This equals 180, because that is the interior angle of the triangles, right? A plus B plus C has to be 180. So this is just 540 minus 180, which is 360. So the exterior angle sum of the triangle equals 360. Okay? And what we'll see is that the same thing happens for all polygons. So the last thing to think about is, what can we tell about the exterior angles of any polygon? I'm going to use a regular we'll say a septagon. Heptagon. Septagon. A regular heptagon that is colliding with something else. So let's pull it down here. Okay, and I'm going to get all these points off of here. Show labels. Okay, so here's what I want to do. I'm going to put a ray in from here to here and just start to get my exterior angles marked. Notice I'm doing them all in the same direction, so it's like the spokes of a wheel that are going in the same direction, not colliding with each other, going this way. See, if I started to go that way, I'm going to get a collision way up here. See up there? So I want to go the other direction to keep everything the same. Okay, so that's what a nice little set of exterior angles looks like. Now, what I want you to recognize is we've already learned how to measure this angle right here. We've already learned how to measure, how to measure that one. We just did that, okay? But if we can tell that one, notice what's going to be the exterior angle. What is going to be this exterior angle right here? It's just going to be the supplement of it. So no matter what type of situation you're dealing with, you're always going to have 180 minus that interior angle is going to give you the exterior angle. Of course, for a regular polygon, you can just then multiply by n and figure out what your exterior angle sum is as well. So let's jump over and do some examples. So our last step here is to do some examples. Find the interior angle sum for each polygon. Well, we did this one already. 180 times 5 minus 2 gives us 540. Okay. Here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's going to be 180 times 11 minus 2, which is 180 times 9, which I actually don't know off the top of my head, but calculator says it's 1620 degrees. Okay. Same thing for any of these. Find the measure of one interior angle. Okay, so let's do this. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be that same 1620 that we found out before, but now we're dividing it by 11. So each middle one, each interior one, is 147.27 repeating degrees. Okay, it's easy. Find the measure of one exterior angle of each regular polygon. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So we got to find the interior angle in order to be able to find the exterior angle right there. So the interior angle is going to be, so each int angle is going to be 180 times, how many did I say? 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 2, all of that over 8. So that's 180 times 6 divided by 8 is 135. And so if that's 135, then the exterior angle is 180 minus 135, which is, I don't need the calculator for that, which is 45 degrees. Okay? Hope you enjoyed it.